Hello and welcome back. In this lesson, we're going to take a look at how to extract information and make calculations and analysis from a simple harmonic motion oscillator graph. So first thing we really ought to know is let's make sure that we understand our basic graphs, okay? A simple harmonic motion oscillator is going to exhibit one of four possible graphs. Let's just sketch them out so we know. The first one is a sine graph. Now, in a pre-calculus math class, a sine graph has a domain of all real numbers, which means it extends forever in the positive and negative direction because the x-axis is a measure of angles in radians. In physics, a sine graph is usually a function of what's called a parametric equation. So in other words, it's going to be velocity, position, or acceleration as a function of a third variable, time. So time can never be negative, and time always starts at zero, or at least potentially starts at zero. So for physics, a sine graph begins at zero and goes on potentially forever as long as the oscillator moves back and forth. So for a sine graph, let's see, if we repeat this one time, two times, t stands for period. So if we would repeat this once, twice, keeping the same amplitude for both cycles. Okay, that's your basic sine graph. Now, sometimes you have to draw what's called a negative sine graph. So just understand, when you have a negative sine graph, you're simply reflecting the graph about the x-axis. That means your graph should instead of starting at zero going up, it should start at zero going down and repeat as many times. Now you also have to be able to draw and recognize a cosine graph. Now, if this is our one period and this is our second cycle or second period, a cosine graph starts at the amplitude position and returns to the amplitude position each time it's done with a cycle, like that. Versus a negative cosine graph, a negative cosine graph would start at the negative amplitude and return to the negative amplitude for each cycle. The period t represents each cycle that is made. So a negative cosine graph would look like this. So the first thing you ought to know is, what are your basic sine and cosine graphs going to look like for this? It's not very involved mathematically. You just need to know what they basically look like. Now, you do need to be able to extract other information, such as the period of the graph. You should be able to come up with the amplitude of the graph. Okay, those two things can be taken right from the graph. Now, from that, you can figure out other things, such as the frequency. You can figure out the angular frequency, otherwise known as the Greek letter omega. You can figure out the spring constant if your oscillator happens to be a mass spring system. If your oscillator happens to be a pendulum, you can figure out the length of the pendulum. So there's a lot of things you can figure out and calculate your way through. You can calculate max velocity, max acceleration. You can also, given this, figure out a function, position as a function of time, which means you can then figure out velocity as a function of time and acceleration as a function of time. So there's a lot of ways you can go about doing this and a lot of things you can figure out along the way. You can also figure out energies. You can figure out max kinetic energy at equilibrium. You can figure out max potential energy at amplitude, or the energy at any point in between amplitude and equilibrium. Okay, a lot of things you can figure out. Not to mention, you can figure out the period of the oscillator in general, using a calculation by, let's say, changing up the mass on a mass spring oscillator or changing up the length on a pendulum oscillator. Let's take a look at this specific example. Below is a graph of position versus time for a 100-gram block undergoing horizontal oscillations at the end of a spring. Answer the questions below about the mass spring system. So the first thing I'm going to do is I'm going to draw where this is. Now, where is the block? The block is at time equals 0, the block is at amplitude. Okay, so what I'm going to do is I'm going to go down here and I'm going to draw a wall. I'm going to draw a surface. And underneath the surface, I'm going to draw x equals 0. That's the equilibrium position. And over here, this would be my positive amplitude. So x max is my positive amplitude. So amplitude over here would be positive 4 centimeters. And if I go the same distance inside the equilibrium, my other amplitude would be negative 4 centimeters. And I can see that my amplitude, my object is starting at positive 4 at time equals 0 seconds. Therefore, my picture might look like this. Long stretched out spring with a mass right at 4. Okay, this would be where the object is as it's ready to go. Okay, so a couple of things that we can get from this. We can figure out the period of oscillation by looking at one cycle. So if I were to look at one cycle, it goes from here and it repeats, I could figure out the time. Now, from the look on that graph, I mean, it's about 0.8 something or other. That's a little bit tough to tell. So here's what I'm going to do instead. I noticed that over at about 5 seconds, it has a very clear indication that I can get a certain number of cycles in 5 seconds or a certain number of cycles in 10 seconds. Okay, so looking at this clearly, I can see that I go through 1, 2, 3, 4, 5, 6 cycles in 5 seconds. So the period of oscillation would be 5 seconds for 6 cycles, which is about 0.83 seconds. I was close when I said 0.8, but this is a more specific way to do it. Or I could have gone 10 seconds for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 cycles. Get the same thing. 10 seconds for 12 cycles also gives us 0.83 seconds per cycle, or 0.83 seconds. The frequency. Well, a couple ways we can get the frequency. The frequency is the inverse of the period. So I can go 1 over 0.83 seconds. I can get it that way. And I get about 1.2 hertz. Now, another way I could get that is I could simply take the inverse of my fraction. In other words, I can go 12 cycles in 10 seconds. Or 6 cycles in 5 seconds. Either way, I still get the same thing. 1.2 cycles per second, or 1.2 hertz. What is the amplitude of oscillation? Well, the amplitude is how high or how far the object goes from equilibrium in either direction. You can see it's a maximum of 4 centimeters. So the amplitude is equal to x max, which is 4 centimeters. Now I'm going to write my answer in meters, which I have to move the decimal twice to the left, because I'm going to need a meters measurement to make the calculation later on. What is the spring constant? Well, the spring constant, I have a mass of 100 grams. I'm going to need that, okay? So I've got a mass of 100 grams. Now, I need to convert from grams to kilograms, so I should move that 3 to the left. And my mass is 0.100 kilograms. Now, how do I get the spring constant from this information so far? Well, it turns out that the value known as the angular frequency, right, is equal to 2 pi over whatever the period is. And what we did is, in class, we derived an idea and an expression that also relates omega, the angular frequency, to the square root of k over the mass, Or we could have written it as omega squared equals k over the mass. Multiply both sides by the mass. And we have k is equal to mass times omega squared, or 0.100 kilograms times omega. So we're missing that. Okay, now how do we figure out omega? Let's figure that off over to the side here. Omega, again, is equal to 2 pi over the period. Okay, now the period's 0.83 seconds. I could go 2 pi over 0.83, or I can go 2 pi times the frequency, since 1 over the period is the frequency. Now that might be an easier calculation to do because the frequency is 1.2 hertz. So 2 pi so if I go 2 pi times the frequency of 1.2 hertz, I get approximately 7.5 radians per second. Okay, it's a little bit more than 7.5, but that's a good enough to round it. So I'm going to go 7.5 radians per second squared. So to make this calculation happen, go 7.5 squared times 100 times 0.100 rather. And we're looking at a spring constant of roughly 5.6 newtons per meter. How much elastic potential energy is stored at maximum amplitude? Well, U max is equal to 1/2 K times X max squared, or 1/2 Ka squared. So that would be 1/2 times 5.6 that we just found, times the amplitude. Remember when I said we needed to put the amplitude in meters? Well, this is where we need it. So we're going to go 0.04 squared times 5.6 and then take half. 0.04 squared times 5.6, take half, is roughly about 0.00448 joules. Now, this maximum potential energy also happens to be the maximum kinetic energy for the mass going through equilibrium. So we can figure out the maximum speed two ways. I can either go K max equals 1/2 mv max squared, use this potential energy as maximum kinetic energy at equilibrium, and solve for V. V is equal to the square root of 2 times K over the mass. I could do it that way. Or I could remember that V max is equal to A times omega, which would be A 0.04 meters times omega 7.5 radians per second. Slightly more efficient way to do it. 0.04 times 7.5 is roughly about 0.3 meters per second. And in the last part here in question 8, we have changed the mass to 250. So the mass is now 2.5 times larger. How is the new period and new frequency going to happen with that? So period of a mass spring system is 2 pi times the square root of m over k, or 2 pi times the square root of 0.250 kilograms, remember we got to change that to kilograms, over the same k of, same spring, same k, of 5.6. Okay, so we go 0.250 divided by 5.6, take the square root, times by 2 pi, and we get roughly about 1.33 seconds. Okay, so what basically happened is if we make the mass 2.5 times larger, the time it takes is about 1.5 times longer. In other words, the square root of 2.5 times is 1.5. The frequency of that, of course, would be 1 over the period, or roughly about 0.75 hertz. Okay, so now let's take a look at position, velocity, and acceleration time simple harmonic motion graphs. As you can see, in part 9, we've already been given the position time graph. We need to come up with the velocity and the acceleration time graph. The great part about this is it's very easy to do this if you have a few patterns in mind. Let's talk about some of those patterns. Feel free to pause and rewind as needed. First, let's talk about 3 very basic simple harmonic motion patterns. These are patterns you can do to not only generate position, velocity, and acceleration time functions, but they will also assist in helping to come up with the graphs associated with these functions. Number 1, position, velocity, and acceleration functions and graphs always alternate between sine and cosine. So for instance, if our position graph is a cosine function, our velocity graph will be a sine function, and our acceleration graph will again be a cosine function. So we always alternate between sine and cosine functions. Pattern number 2. As we alternate functions and we go from position to velocity to acceleration, we will tack on one more factor of omega each time. We will multiply by a factor of omega every time we do this. I will demonstrate above in just a moment. Last pattern, as we transition from sine functions to cosine functions, the sign of the function stays the same. So in other words, if we started with a positive sine function, it remains a positive cosine function. If we had a negative sine function, it stays a negative cosine function. So the sign stays the same when we transition from sine to cosine. When we transition from cosine to sine, however, the sign switches from positive to negative or negative to positive. Let's take a look at these patterns in action. The very top, let's go ahead and draw. Let's write the position as a function of time. Okay, so the equation for position as a function of time would be x equals a cosine omega t. And I know it's cosine because we can see that our graph is starting at time equals 0 at the upper amplitude. Well, what about the velocity and acceleration graphs? Let's follow those patterns. One thing we should know about all 3 graphs is that the period of the function remains the same. That means the time it takes to repeat each part of the wave remains the same. Therefore, if the period remains the same, then omega, which is 2 times pi divided by the period, will also remain the same. So since the period of the function remains the same, omega remains the same. So every function is going to have the same omega t. Okay, so now let's take a look at what we learned. Pattern number 1, we alternate between sine and cosine functions. So if I'm starting with a cosine function, my very next one needs to be a sine function, and then back to a cosine function. Notice I have the same omega t after each part of the function, or as part of the function. Now the next part is when we go from cosine to sine, the sign switches. So since this was positive, this becomes a negative. And as we go from sine to cosine, the sign remains the same. Since it's negative, it stays negative. The last part of the pattern is we tack on and we multiply by one factor of omega each time. Now you might be saying, well, okay, there's no omega here. Well, technically there is. Multiplied times a is omega to the 0 power. Remember, anything to the 0 power is 1. So this next one becomes a times omega to the first power, which is just a omega. And the second one would be a times omega to the second power. So you can see we're tacking on one more factor of omega each time. Now, for our specific problem here, we had, I'll write this next to each one, x was equal to 4, I'm going to write it in terms of centimeters, cosine of 7.5t. Okay, and you can see my upper and lower limits are 4, right? My velocity graph is going to be negative. Now, I need negative a omega. Now, you might remember a omega is my maximum velocity. So let's go back to the previous part, and we might recall that our maximum velocity was calculated at 0.30 meters per second. So negative 0.30 sine of 7.5t. And then our last one is A is equal to negative, and let's see, I don't believe we calculated a maximum omega, so we can do that right on the spot. A max is equal to A times omega squared. So the amplitude was 4 centimeters times 7.5 radians per second squared. Okay, so if we multiply that, we get about negative 230 centimeters per second squared. We can make this look like negative 230. We're back to cosine of 7.5t. All right, so why am I bringing this part up? Well, to come up with the graphs now, we talked about the function patterns. What about the graph patterns? To come up with your graphs, you really only need to know 3 things. These are the patterns, steps, and patterns for producing simple harmonic motion graphs. Number 1, set up the amplitudes first. Okay, these are the max values. Okay, and set them up with horizontal asymptotes. So what I'm going to do is I'm going to give this graph a scale. Since my largest is going to be 0.30, now do keep in mind that that's 0.30 meters per second. So what I'm going to do is I'm going to rewrite this as 30, because we're doing centimeters per second, so negative 30. So that would make this 10, 20, 30, negative 10, negative 20, negative 30. And what I'm going to do is I'm going to create horizontal asymptotes like that. Okay, and then I'm going to do the same thing with my next graph. Get my next graph set up. My maximum acceleration is 230, so I might go 100, 200, 300, and then the same thing down below. Okay, which means I would probably cap it off at about right here at positive 230 and about negative 230. And you're going to have to estimate, obviously. Okay, now what that does is that keeps you focused on how high and how low your wave can go. The next part of this is know the basic trig function for each graph. So if you know the basic trig graph, in other words, you know what a sine function looks like, a negative sine, a cosine, or a negative cosine, if you know what these basic functions look like, you're always going to be able to figure this out. Okay, so for instance, I know that this is supposed to be a negative sine function. Now, negative sine functions look like this, as opposed to their sine counterparts that look like this. The problem is I can't just draw any old negative sine function. Because my period of the velocity function has to match up with the period of the position function, and so on. So that would be my next part. Make sure all three graphs have the same period. Okay, so here's how we can do that. What I like to do is count where I have maximum values. Okay, so in other words, here, 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 and I count 7 times between 0 and 5. Okay, 8, 9, 10, 11, 12, 13 times if we're going all the way to 10. Well, what I'm going to do is I'm going to put those same 13 locations right here. Here, 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 and here. And what that means is these are the points that you have maximum displacement. But they're also the places where you're going to have zero velocity. So you need to make sure that you can see that we created one full cycle here. Well, we need to make one full cycle happen here. So this is what the velocity graph will now look like. You got to take your time with this one because it's kind of difficult. So a negative sign graph goes down, up, repeat. Down, up, repeat. You just keep doing this the whole time. And you can see I'm creating a negative sign graph that is completing a cycle passing through each one of those dots. Each one of those dots represents the location for the maximum potential energy and the maximum displacement, but also the minimum or zero velocity. There we go. Those are all my cycles. A little bit messy here in the middle, but take your time, you'll get it. Okay, acceleration graph is really no different. This time, you're producing a negative cosine graph. Well, you know that a negative cosine graph looks like this. A negative cosine graph is just reflected about the x-axis. So how do we draw this? I take those same dots, put them in the same location, but now they're going to be down here, because that's where the cycle's going to repeat. Okay, and all I have to do is just simply repeat my graph every time I get down to that part. So like this. And we have ourselves a negative cosine function. When you have this many cycles, it becomes a little challenging to try and fit them all in nice and neat. So obviously do your best. And that's what's needed to put together velocity and acceleration simple harmonic motion graphs.